Today we are going to solve Leetcode 111, that is minimum depth of binary tree. So in this question we are given a binary tree and we have to find the minimum depth of the binary tree. Minimum depth is the number of nodes along the shortest path from the root node down to the nearest leaf node. And a leaf node is a node with no child tree. So let's see how we can solve this question. So as we know, we are given a binary tree and we have to find the depth of it. So we know that we have to traverse this tree to find its height. Now when it comes to traversal, there are two types of traversal that we do. And first one is DFS and second one is BFS. So let's try to solve this question using DFS first and then we will go through BFS approach as well. So if I have to traverse this tree in DFS order, depth first search order, so how I'm going to know that what is the height of a node? That is the first question, right? Firstly, I have to find the height, and after getting the height, I want to return the minimum height. So how I'm going to know that this node or this node is having minimum height so and so? Suppose if I'm standing here, so what is the height of this level or this node? This node's height is going to be 1. This node's height is going to be 1, right? Now if I'm saying what is the height of this node whose value is 20. So firstly, the node itself is having a certain height, right? So we'll consider it as 1. And secondly, the height of its child node is going to be added to it. So what is the height of its child node? That is also 1. So this will be 1 plus 1 equivalent to 2. So I can say on the basis of the right child, I have calculated this node's height as 2. But if I'm going to consider the second child as well, so in this case we know that its height is also equivalent to 1. And if I'm going to say take minimum or maximum of both the values, as per this question what we will be taking minimum, right? So if I'm saying this is height 1 and this is also height 1, and to calculate the height of their parent node, what I will be doing, I will be taking the minimum of left and right subtree's height. In this case both are similar, but there might be a case where suppose this 7 would have extended with some more nodes. So in that case, what is the minimum one? Minimum will be the left subtree, right? So in that case, what will be the height? Height will be 2. So that's how we calculated the minimum height of this node, right? Similarly, we will proceed to root node and again we will do the same thing. Root node's height itself is 1, that level of the node is 1, and we will add the child's height as well. That level is 1, and we will add subtree's height as well. So what we will do, we will again take the minimum of left and right subtree, and in this way we will get the root's height. So in this case we know that this subtree's height is 1, and when we are going to check the minimum, we are going to get minimum of 1 and minimum of 2. This is the 2, right? So what will be the value? Value will be 1. So 1 plus 1 will be 2. So the minimum height of this whole tree is 2. So this is how we will be solving this question using DFS. What will be the time complexity of this whole approach, where we are going to leaf node and then checking the height of each and every node and returning the minimum height and adding it with the node height itself, which is 1 in every case. The time complexity of this whole DFS approach will be big O of n, because we are traversing each node once, right? And what will be the space complexity? Space complexity of this approach will also be big O of n. Why? because we are using recursive approach, right? We are recursively going to call these nodes. We are recursively going to call these child nodes and calculate its height. So for that reason, we will be having a call stack, and call stack is going to contain all the calls to these nodes that we have made. So in that case, space complexity will also be equivalent to big O of n. Now let's try to understand BFS approach, and then we will code both the approaches. So if I'm saying let's try to traverse this tree using BFS, so how I'm going to do this thing? Firstly, I will come to this node. Here I'm saying height is 1 again. Then what I will be doing, I will be storing this node and this node, both the children of this node, in a queue. We know that in BFS we use queue. So 9 and 20 will be in my queue. Then what I will say, now let's change the level. So I will go to this level. Now what I'm saying, take out the node from our queue. So I did that. Now check if this node is having child or not. So we can see that this node is not having any child. And because we are traversing this tree in level order traversal, so we know that once we encounter a node with no child node, that is a leaf node, right? So now I know that 9 is a leaf node, and I know at this level the height is 2, right? So I know that when the height is 2, I encountered a leaf node that is 9, and I know that the minimum height will be equivalent to this only, 2, because this is the first node, which is first leaf node, and if I'm going to traverse furthermore, that won't be the minimum height. Minimum height is this one only, because I am traversing this tree using BFS, so I know I already traversed previous level and traversed all the nodes of that level. So if I hadn't find any leaf node in my previous level, and in current level I am having a node, this is the minimum node. I don't have any doubt in this case. So what I will do, I will right away return the height, and this will be the minimum height. So in BFS we came to know that we are not even going through these nodes, right? Why we are not going through these nodes? Because we already know that the first node, first leaf node that we will encounter in any of the level will be the minimum height, right? So for this question, my preference is mostly BFS, because if we consider the best case scenario, so we can see in BFS we are going to get the answer faster, I would say. We will get our answer faster. But in worst case scenario, we know that both the traversals are going to perform with same complexity. How we are going to check the complexity? So let's see what's the complexity. Well, complexity is similar to DFS, because in this case as well we are traversing each node once, so the time complexity is going to be big O of n, and space complexity, as we are using this queue, so the space complexity is also going to be big O of n. So complexity wise both the algorithms are same, but if we see the best case, as we already saw a dry run, so in my personal opinion for this question I would prefer BFS, but we will still code this solution using both BFS and DFS. Let's see firstly how we are going to solve this question using DFS. So for DFS we will be having our DFS function, and in that function we will be passing our nodes. So what we said, if it's not a node or it's null, then return 0. If in case there is no left node, then what I'm saying, try to find the minimum of right node. So in that case what I will do, return the height 1 plus DFS on the right side. right subtree, right? And if in case there is no right subtree but there is a left subtree, root dot left, then in that case what we will return the traversal on left subtree. These are the case where we have no other option. We have only one child node and one subtree. In this case, we will do like this. But if we are having, this will be elif. But if we are having both the childs, in that case, what I'm saying, return 1 plus minimum of DFS on root dot left and DFS on root dot right. So if we are having both the child nodes and both the subtrees, then calculate which one is having the minimum height and return that one. So this was our DFS function, pretty small function. So let's call it from here and pass our root. So this is it. This was the whole DFS approach. Let's try to submit this. We can see this works pretty well. Now let's try to code our BFS solution. So for that we know that firstly we need a queue. So let's define our queue. So DQ will be this. In this DQ, let's just append our root node. This is a root node. Then we know we have to store depth as well. So as our root node is already there, so let's initialize it with 1. Now what I'm saying, run this loop to the point our queue is having node. Now for every level, for all the nodes in one level, what we will be doing, we will be checking, right? For every level we will be checking this. So I'm saying queue dot pop left, and after this what we were doing, we were checking if this is not a node. If this is null, then continue, because we hadn't checked it before pushing, right? Pushing it in our queue. So that's why we are checking it here. If not node dot left. Now what we are checking if this is a leaf node. So if this node is a leaf node, then what I'm saying, just return depth. And if this is not the case, then what I'm saying, just append node dot left and node dot right. And once we are done with one level, what we are saying, just increase the depth by 1. And if in case we didn't get a value or we got a empty tree, if we got an empty tree, so let's just add this here, if not root, then what I'm saying, return 0. If it's an empty tree, then we are returning 0, else we are doing the whole calculation. This is also working, and we can see this is 91% better than other approaches, and the previous one was I think 41. So that's why I was saying that for me BFS is more preferable for this question. Rest, I hope this whole video was helpful for you all, and I will soon come up with few more questions. Till then, you can like this video, subscribe my channel, and I will see you soon with few more questions. Thanks for watching.